We will define the volume as the amount of space that some body occupies. Volume of simpler bodies as cube, ball or a cylinder we can calculate using simple mathematical equations. However, when there is a body with irregular shape, there are no simple mathematical formulas with which we can calculate the volume, so we use other methods. In a graduated cylinder, we have put 3 deciliters of water. We will determine the volume of the utility clamp that we used in former experiments. We see that the water has risen by 3 marks. The difference in volume is exact to the volume of immersed clamp. 1 mark represents 1 milliliter, which is equal to 1 centimeter cubed, so the volume of the clamp is 3 cubed centimeters. In the same way, we can determine the volume of any shaped objects. Now we will do the experiment in which we will demonstrate which forces act on the body after we immerse it in some liquid. Let's hang the mass of half a kilogram on a Newton meter. It is showing a weight of 4.9 newtons. Now we immerse the weight in the water. The weight on the Newton meter has decreased from 4.9 to 4.3 newtons. We have defined weight as a product of mass and gravity acceleration. Since neither the mass of the object nor the gravity acceleration don't change, we conclude that now there is another force that acts on the clamp. Since the apparent weight is now reduced, we conclude that this new force has an upward direction. The amount of force is equal to the difference between the real and the apparent weight that we can read on the Newton meter. In this case, the difference is 0.6 newtons. We will call this new force buoyancy. Let's now try to experimentally determine on what it depends. The glass in which we will immerse the weight, we will put in a wider pot and then fill up to the top with water. Next, we immerse the weight in the glass and the excess water will be collected in a wider pot. Volume of the excess water is the same as the volume of the immersed weight. Let's determine the weight of the excess water. We put the overflowed water in a plastic cup. We can see that the weight of this excess water is the same as the buoyancy on the weight that displays this liquid. The weight of the water is displaced as product of its mass and gravity acceleration. The mass of displaced water is defined as product of its density and its volume. Earlier, we have showed that the volume of the displaced water is the same as the volume of the immersed body. And finally, we obtained the relation for the buoyancy on an immersed body. It is the product of the density of the liquid, volume of the immersed body, and the gravity acceleration. When we hang the weight on the Newton meter, there are two forces acting on it. Gravity force in downward direction and the spring force in upward direction. Since the weight is not accelerating, by Newton's first law, these two forces must be the same. But if we immerse the weight in liquid, then there is a third force, the buoyancy. Before immersing, we have two equal forces, gravity force in the downward direction and spring force in the upward direction. After we immerse the weight in water, buoyant force starts acting on the weight in the upward direction. The weight is not accelerating, so by applying the first Newton's law, we conclude that the gravity force is equal to the sum of elastic spring force and buoyancy. That is, the elastic spring force reduces exactly by the buoyancy so that their sum stays equal to the gravity force. As we have shown before, buoyancy on some body is the product of the liquid in which that body is immersed volume of that body, and the gravity acceleration. Substituting this in former equation, we obtain the following expression. From this equation, we can express the density of the liquid as difference between the weight of the body and the Newton-meter force when the body is immersed, divided by the product of gravity acceleration and the volume of the immersed part of the body. We can conclude that all we need for determining of the density of the unknown liquid is the Newton meter and the weight of known volume. Let's try to verify this conclusion by using it to determine the density of water. Density of the water is given as the difference of the weight of this body, 4.9 newtons, and the force that Newton meter shows when we immerse the body in liquid. That is 4.3 newtons. We divide it by the product of the gravity acceleration, which we know is about 10 meters per squared second, and the volume of the body. The volume of this weight is 60 milliliters. That is 6 times 10 to the power of minus 5 cubic meters. When we calculate this expression, we obtain 1000 kilograms per cubic meter for the density of the water. The same as the data in the literature.